All right, welcome back. We're continuing to work on separable differential equations with these four problems. Now this one looks maybe not so much fun, but I think you're going to notice we got an x value over here. We got to move it over there. We got to move these y values over here. But remember, they have to be multiplied. They have to be separable. They have to be multiplied together. Well, hopefully you notice there's a y in both terms. When we have a y in both terms, we can factor them out. I'm going to change the y prime to dy dx. I'm going to factor out this y to make it 2x plus 3. Now we're going to separate them. So both of these x values have to move over to this side, and this y value has to move over to this side. So I'm going to skip a bunch of steps. I'm going to write what I know is next. Okay. So I'm going to multiply both sides by dx and divide by x squared plus 3x and divide by y. So I'm going to end up with this. Whoops, I'm not going to end up with that. So I'm going to end up with this. Remember that dy stays, and I'm dividing by y to bring it over. This 2x plus 3 stays. However, this x squared plus 3x, I'm dividing by it. And this dx comes over here. All right, separated. Agreed? All the y's and dy's here, all the x's, dx's here. Once it's separated, integration time. This integral we've done quite a bit. That's the natural log of y. Now this one, we just can't integrate it because you only know certain things. You know the power rule, and you know trigs, and you know e's, and you know logs. You do not know, there's no quotient rule for integration. So you're going to learn the only technique, the one other technique that you learned, which is integration by parts. So we're going to choose a value to substitute. We call it u substitution generally. We're going to let u equal x squared plus 3x. Because what's its derivative? 2x plus 3 dx. And guess what we got right here? We've got 2x plus 3 dx. So let's rewrite it now. Let's go back to our purple. So that's going to become u. This whole 2x plus 3 dx is going to become du. Remember when we do this, that u is the x squared plus 3x, and this du is the 2x plus 3 dx. All right, now that we have that, can we integrate this now? Because really this is just 1 over u du. The integral is the natural log of u plus a constant. Now, we don't want to leave it u. We're going to turn it back into x. And remember, u was x squared plus 3x. So this is going to be the natural log of absolute value of u equals the natural log of x squared plus 3x plus a constant. Now that constant is going to go some changes again. I'm going to make it c1 for now. All right. Well, they are natural logs. The only way to eliminate a natural log is with the function of e to the x. So e to the natural log of y is y. E to this would just be x squared plus 3x. And we're adding So when we add exponents, it means we're multiplying. So when we write it in its final form, we're going to write this is a capital C x squared plus 3x. That's the solution. Now if you want to, multiply it or take the derivative of this. You'll find when we take the derivative of that, we're going to end up with that original equation right up there. Okay? That's the solution to the separable differential equation. Okay? 3 more to go. All right. Let's change that to dy over dx. Doesn't look so bad. Is there a kink in it? Why would he give one that looks a little easier than the last one? Well, he could be getting older. Or he could be trying to show you something. We'll find out. All right. So I'm going to move the dx over here and the y over here. All right. Separated? Yes. So differentiation time. This one's pretty easy. X squared. Well, I'll put C1 to see if we do anything funny with it. What's the antiderivative of this? All right, your first thought, which is correct, since it's just a y to the first power, it is going to be the natural log of 2y plus 1. But that's not the only thing. So if I take the derivative of this, I end up with 1 over 2y plus 1 chain rule times the derivative of 2y plus 1, which is 2. So there's a little 2 I got to deal with. So we're going to move this over to the side for a second. Okay, we'll put that right under me. And I want you to think about this using u substitution. Okay. I'm going to let u equal 2y plus 1. Now I'm going to do it over here where I've got some room. So I'm going to let u equal 2y plus 1. So its derivative is 2. All right. Well, so my 2y plus 1, I've got. My 2y plus 1 is right here. I have a 1 dy. Well, I don't need a 1 dy. I need a 2 dy. So remember what I showed you? One of the ways to do it. If I need a 2, give it a 2. And how do I undo a 2? By dividing it by 2. 2 divided by 2, these would cancel out. So now I built in what I need. My 2 dy is right here. Well, there it is. My 2 dy becomes du. So when I rewrite this, it's going to be 1/2 of, this is going to be du, and this is going to be u. Okay. I'll scoot this down a little bit. What's the antiderivative of 1 over u? Natural log of u. But remember, we don't want natural log of u. What does the u actually equal? 2y plus 1. Now, we originally said it was going to be natural log of 2y plus 1. But what extra thing did we need? We needed the 1/2. You might notice a little shortcut for this one. If it's a single power, it's its first degree equation, 2y plus 1. If you take its antiderivative, it's 1 over 2y plus 1. I'm sorry, it is 1 over 2y plus 1. It's the antiderivative natural log of 2y plus 1. And what's the derivative of 2y plus 1 is 2. So when we take the derivative, we multiply by 2. But since we're taking the antiderivative, we divide by 2. Now I showed you this before we were separated, when we were still together. And it only works when that is a constant. If it is a variable, we gotta find a different way. So hopefully you'll remember that. But here you go. Here's our antiderivative. Now before I deal with this e, I'm going to multiply both sides by 2. It will just make it a little bit easier. All right. Now let's do the e thing to it. I'm going to e to all of this. So e to the natural log, this is just 2y plus 1. E to this, so I'm going to try to make this one step now. It's going to be e to the 2x squared times e to the 2c1. Remember, and that e to the 2c1 is just going to be some constant. So some constant times e to the 2x squared. Okay? Because remember, this e to the 2c1, this becomes this. Okay? That's the key, because that's going to make the next section a little bit easier, because we're only going to do that one time. So there we go. So just do the normal things we would do. Subtract 1 divided by 2. So c e to the 2x squared minus 1. And then we're going to divide by 2. So 1/2 c e to the 2x squared minus 1/2. Now you might be thinking, well, that's just 1/2 a constant. Can I just make that another c and things like that? You could. You could. But since I've already made it a c, we're just going to kind of keep it like that. There's your differential equation. All right. 2 more. We've added some information in here now. What I've added is this. Here's my separable differential equation, but I'm giving you an initial condition. How does that affect, how does the initial condition affect it? Well, you figure it out. It tells you the c value. So I'm going to start with this. It's already dy dx. So I don't have to rewrite it that way, although I just did rewrite it. Okay. Now how do I separate these things? Well, it's almost like cross multiplying. I'm going to multiply both sides by y squared. I'm going to multiply both sides by dx. Separated? It is. Once it's separated, we can integrate it. So the antiderivative of y squared is 1/3 y cubed. Antiderivative of x squared is 1/3 x cubed. Antiderivative of 4x, I'm going to raise it by 1, 2, divided by 2 is 2x squared plus some constant. All right, everybody with me? Antiderivative, antiderivative, antiderivative plus c for the constant. So it doesn't matter when I do it. I can put this in right now. I can wait and do it later. What's easier? I'm not sure. I think in this case, it might be easier to find the c right now. Because remember, x is 0 and y is 3. So let's plug it in there. So y is 3, right? So we're going to have 1/3 3 cubed. That's a lot of 3's. And what is 1/3 times 0 cubed? And what is 2 times 0 cubed? And the c stays a c. All right, let's figure this out. 3 cubed is 27. 27 divided by 3 is 9. All right, our c value is 9. We end up with this. We've got it now. Like I said, if we can solve for y, we should. This won't be too bad. We just got to multiply by 3 and take the cube root. So we multiply everything by 3. And finally, the inverse of y cubed is a cube root. And there's our answer. No plus c value anymore because we figured it out. Whoa, big, whoa, 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 whoa. Try that box again. I get a little crazy sometimes making these upper boxes. All right. That's our separable differential equation. Remember, they got to be multiplied together to be separated. You separate them, integrate them, solve for y. All right, last problem. Here's our differential equation. There's our initial condition. Let's go. And hopefully, we'll see what happens. We'll see how easy it is. I don't know. We'll change y prime. Oh, wait a minute now. We have a y prime on both sides, don't we? Oh, man. I'm not going to change to dy dx just yet. All right. Remember, there should be multiplied together. These are being added. We got an issue. So how can we get this y prime over here before we separate it? I'm just going to do this. Subtract it away. All right. What do you see? How do I simplify this one? Well, let's distribute that through. It'll be y times y prime. And the reason I didn't change it to dy dx yet is because I didn't want to write dy dx 1,000 times. All right, y times y prime. What's 1 times y prime? Minus y prime. 2x minus 8. Oh, see how sneaky that was? What does this become? This just becomes y times y prime. Because these subtract away to be nothing. These become 0. Now I have that. Isn't that nice? That worked out nice for us. All right, now I'm going to change it to dy dx. All right, now I'm going to separate them. Whoops, that would be wrong. The x comes over here. Y's, x's, integrate. Okay. Antiderivative of y, we'll put that up here, would be 1/2 y squared. Antiderivative of 2x minus 8, antiderivative of 2x, raise it by 1 becomes 2, divided by 2, we get, so that's x squared. Antiderivative of 8 with respect to x is 8x plus some constant. I'm going to put it c. Oh, wait a minute now. Plus some constant. I don't need to make it a c sub 1 because I remember from up here, f of 0 equals 8. I know this is true. I know that when x is 0, y is 8. Well, let's find c right away. 1/2 of 8 squared. 0 squared is 0. 8 times 0 is 0. Plus c. 8 squared is 64. Half of 64 is 32. All right, c is 32. So what do I have? I have this. Okay. Now, move this down a little bit. Okay, I want you to remember. Well, not remember. We got to solve for this. So I'm going to solve for this. So I got to multiply everything by 2. So it's going to be 2x squared minus 16x plus 64. Then I'm going to shoot that answer over here. That answer is going to be the square root of 2x squared minus 16x plus 64. Now, one more thing to think about. Initially, we had a problem like that where we put a plus or a minus because we didn't know if it was going to be the positive or the negative. But these are supposed to be, because it says f of 0 equals 8, this is supposed to be a function. So a function has to be either the plus or the minus. Which one? Well, your answer is right here. When I plug in 0, I need to get a positive answer. So guess which one I don't need? I don't need that negative. I just need to have a positive answer. Now let's put a plus there. We assume it's a plus. So in this case, it's not plus or minus the square root. It's just the positive value because this answer was positive. If I plug in 0, will I get 8 for an answer? Sure enough, 0 minus 0 plus 64, square root of 64 is 8. This satisfies this differential equation. All right, there it is. Differential equations are over. So just want to leave you with one more thing before you go. I know I promised I wouldn't do it, but I can't help myself. You gotta keep them separated. You gotta keep them separated. Okay, sorry. Just went through my head again. So, you know me, sometimes I just can't help myself.